Okay, so hello everyone. Um, I'm Jun and welcome to E405. Today, what I'm gonna talk about is robotics fundamentals. So in this lecture, I like to focus on, the kind of principles of robotics. So basically, what we wanna do in E405 is we wanna make robotic applications. We have mobile robots, and on top of the mobile robot, we have a robotic arm, and we are gonna do like some manipulation task, right? So that's a kind of application. But this application can be only built on top of a robotics foundation. So this foundation means robotics theory and recent AI algorithms. So in this lecture, basically we are going to focus on this robotics foundation part. So here's the contents. Uh, One big part is basic robotic terminologies. terminologies, because basically what we do is we use robotic system. So we have to know some basic robot things, right? So I'm gonna cover some very important terminologies, and then I move on to something called rigid body kinematics and robot manipulator kinematics and pose estimation and so on and so forth. But I'm not gonna follow the order in today's lecture. I'm gonna focus on this rigid body kinematics and manipulator kinematics. So basically, I'm skipping this part, okay? Uh, because the next week, in the lab session, this part is more relevant. So in the first lecture, I'll just jump into this rigid body kinematics, manipulator kinematics. And in the next lecture part, I will I'll start from this robotic terminologies, and I will jump to object pose estimation using markers. Right? So let's jump. Let's jump to uh, the rigid body kinematics. So here we are basically going to study rotation matrices and homogeneous transformations. So if you have ever studied, I don't know, computer vision um, or like kinematics from mechanical engineering, I think you then know what's a rotation matrix and homogeneous transformations. If not, this might be the first time, but I'll try to deliver every important things. Okay. Right. So what is rigid body? So basically, we are doing rigid body kinematics, right? So what is rigid body? So in physics, rigid body is a solid body, okay, in which deformation is zero, right? So let's say this is a rigid body. Then the distance between this point and this point, so basically any 2 points, distance is fixed. So even if you try to squeeze, apply force, okay, squeeze an object, it never deforms. Never deforms. Instead, distance between these 2 points is fixed. Okay, so distance between any two given points on a rigid body remains constant, regardless of external forces or moments. Okay. Okay, that's basically the definition. Um, so the robotic systems, something like this, even your system, your manipulator, is just a connection of rigid bodies. Connection means connecting rigid bodies using joints. Okay. Okay, but rigid body is a body. It's just a moving object in the space, right? So we have to represent rigid bodies in numbers. Otherwise, we cannot calculate, right? We cannot calculate like positions, velocities, accelerations, something like that. So we have to introduce a coordinate system, right? By the way, what's the difference between rigid body and point mass? Um, Rigid body is really a body, something like this, and point mass is this one, right? Rigid body, point mass. So basically, point mass can only translate. It can only translate. There's no such thing as a rotation. Okay, rigid body can both translate and rotate. That's the main difference. Okay. So anyways, we have to introduce coordinate system. I think everyone is familiar with what's a coordinate system, right? So in space there's a point, all right? So there's no way to represent point. So what's the position of the point, right? We cannot represent. So we have to introduce a coordinate system, this X and Y coordinate system, right? And then we can assign numbers to point P, right? So this is X coordinate and this is Y coordinate, right? So point X, this is X, Y, then the position is X and Y, something like that. Oh, actually it's PX and PY here. PX and PY. You can assign numbers. If you take differentiation, then that's velocity. Once again, then that's acceleration. And then using this coordinate, we can start like calculate some things, right? Extension to 3D is very straightforward. So instead of having two axes, we introduce X, Y, and Z, the third axis, then that becomes three-dimensional, right? So point P in the space, perhaps Px, Py, and Pz. It's easy, right? So it's in robotics, it's very important to understand the concept of body frame. So body frame. So what is there are two different types. First one is world reference frame, and second one is body frame. So world reference frame is inertial frame. I think we are all familiar with what's an inertial frame. That's kind of fixed reference. Okay. Or sometimes it's called global frame, universal frame, or something like that. Reference frame, right? It has many names, but it's the same. They are the same. So I think I don't have to explain what's a reference frame. Body frame is here. It's in robotics. It's very common to attach a frame to a rigid body, okay? And that's called body frame. So let's say this is a rigid body. Okay, and here's reference frame. It's a reference frame, and that is fixed. It never moves, okay? It gives us kind of global position. In this rigid body, we often attach a frame to a body, okay? So this frame is attached to the rigid body. So if this body, rigid body translates something like this, then this body frame translates together because this body frame is attached to the body, okay? If this body rotates, something like that, then this body frame also rotates, should rotate, right? Because this body frame is attached to the body, okay? So basically, rigid body kinematics is identified by coordination of the body frame. Okay, we just follow the body frame. I mean, we just track the body frame. Right? So we have to represent translation between two frames. Two frames means reference frame and body frame. So before like representing translation between two frames, we know how to point or represent a point in a space, right? So there's a point P, and then this arrow, this vector represents the point, right? Simple. What about two frames? So let's say this is reference frame, and this is a body frame. So there's a body, okay? So this is reference. That means reference is fixed on the world, right? And body frame is fixed on the body, rigid body. So a vector pointing this frame with respect to the reference frame is a vector pointing the origin. Okay, that's the translation between two frames. Very easy, right? Before going to the rotation, I have to tell you the notation. So this is a vector R pointing P with respect to frame 1, okay? With respect to frame 1. And this vector is pointing P, okay? So this one is a vector pointing the origin of frame 2, origin of frame 2, frame 2 with respect to frame 1, with respect to frame 1, okay? That's the notation. All right, here's the rotation matrix. So now we have two frames again, frame 0 and frame 1. And their origin is the same, it coincides. And there's a point P, okay? So vector pointing P with respect to frame 1 is, let's say that's an ABC. Okay, it's a 3-dimension space. So we have 3 numbers, right? It's ABC. And here what we want to do is we want to express point P with respect to frame 0. Okay? We know what is this one. Our P from 1, that's ABC. Then what is vector pointing P with respect to frame 0? Okay, that's the question. Right, so the vector pointing P with respect to frame 1 That's ABC by definition or by assumption. This is just like array of numbers. A little bit more. This is in coordinate, right? This actually means A towards the first basis. Which is basically this one, I1. Oops, sorry, that's I1, right? B along the second basis, this one, and C along third basis. Okay, so that's RP1. So we have to basically change the basis. So for RP0, we have to like project everything, right? Everything to the I0 direction, right? So that will be the first component. So we just project everything to the I0 direction or I0 basis, okay? So that's the first component. And the second component is projection of this vector to the second basis direction, okay? And third component is projecting this one to the third basis of the frame 0, right? So the vector pointing P with respect to frame 0, that is the first component, second component, and the third component. And that's basically, right? That's I1, I0, B, J1, I0, C, K1, dot product, I0. That's A times I1 dot product J0, B times J1 dot product J0, something like that, right? So we can just rearrange the terms so that we have A, B, and C here, which is nothing but the first component of RP, 1RP, okay? The first component, and that's the second component and the third component, right? And here's just the dot products of basis vectors, okay? So this is nothing but a vector pointing P with respect to frame 1. And that's a bunch of dot products, which is 3 by 3 matrix. And this matrix is called rotation matrix. And we give a number, rotation from 0 frame to the first frame, okay? And this vector is nothing but 1RP. So common interpretations for rotation matrix, there are like several interpretations, but I like to introduce you 2 interpretations. The first one is rotation matrix actually rotates a vector, okay? This rotation matrix is applied to a vector, then it really rotates a vector in the space, okay? So if you represent this vector in different frame, in some sense, it's rotation of a vector, right? And second interpretation is more mathematic. It's more mathematical, and this is how I like introduced the rotation matrix. Rotation matrix actually changes the basis of a vector. Okay, so here's the vector, the like vector pointing P with respect to frame 1. That means here bases are all like I1, J1, and K1. And if you apply rotation matrix, something like that, then for this vector, our basis is I0, J0, and K0. So it's a change of basis. So these two interpretations are quite common. So we can actually multiply rotation matrices, or we can compose rotation matrices. So here's the first frame and second frame. So from frame 0 to frame 1, let's say we have a like rotation matrix R0 to 1. And here's the first frame, second frame, and here's another rotation matrix that's rotation from 1 to 2. Then what is rotation from 0 to 2? So that's the question. And the answer is we can just multiply these two rotation matrices, okay? And here's something like cancellation. Cancellation. So here, when we multiply rotation from 0 to 1 and rotation from 1 to 2, you can actually cancel out this 1 and 1, one on the bottom and one on the top. And the result becomes 0, the rotation from 0 to 2. Okay, so this cancellation is quite interesting. And this is composite of rotation matrices. All right, so first we saw what's a translation, and then we saw what is a rotation between two frames. Actually, we can combine both, right? We can have translation and rotation at the same time. Okay. Translation is just like it's just translating a frame without rotating frame, right? Rotation, origin is the same. That means there's no translation. There's only pure only pure rotation without translation. But actually, here's frame A and frame B, and you can see there's a translation and the rotation, right, at the same time. And then we apply the same thing. There's a point in the space, and then we have vector BRP, which means a vector pointing P with respect to frame B. Okay. And then what is vector pointing P with respect to frame A? So that is actually a vector pointing P. So basically that's this vector. This vector will be this one. Should I change the color? This vector, the purple one, plus this vector, right? So that has to be A R B plus B R P, right? That's a basic like a vector calculation. However, you have to be careful. What you have to be careful is that this one is represented with respect to frame A. That means basis is in frame A. This one, again, with respect to frame A, but this one is written with respect to frame B. So vector is basically just an array of numbers. I'm just repeating. But that really means A along the first basis, and then B along the second basis, and C along third basis. So if the bases are not the same, if they are different, you cannot really add two vectors. You have to change the basis first, and once the bases are the same, then you can add two vectors. So here you have to change the basis. How to change basis? That's rotation matrix. Okay, so we have to introduce rotation matrix. So that's this formula. So ARP, that's simply ARB, this one, again, this one, plus BRP, which is this one. However, we have to change the basis using rotation matrix. Then everything is written in the frame A, then you can add vectors. So this equation can be actually rewritten as follows. So ARP is ARB, this rotation, times BRP, and plus this vector, right? And this one has no big meanings. So in computer vision, this one has a meaning, but for us, it's really meaningless. It's just for our calculation. So we can just stack a vector, something like that. So that becomes 4x1 vector. So again, 4x1 by augmenting this value 1. And that's 4x4 matrix. Rotation, 3x3. This is translation vector, 3x1. So that's a 0 matrix, 0, 0, 0. Basically, that's 1x3, 1, that's 1x1. So in total, that's 4x4 matrix. And this matrix is called homogeneous transformation. Okay. The composite of homogeneous transformation. So as we did for the rotation matrix, we have frame A, frame B, and frame C. And let's say we know the relation between A and B, and we know the relation between B and C. Then what is relation between A and C? What's the transformation from A to C? Okay, that's just ATB times BTC. So there's kind of cancellation, and that becomes ATC. Okay, and again, that's of course 4x4 matrix. Interesting fact is that, so you don't have to like know this kind of things. Interesting fact is that rotation matrix has this property. And that means rotation inverse is just a rotation transpose. So if you transpose a matrix, rotation matrix, that's actually a inverse. Inverse of homogeneous transformation, that's given like that. So it's maybe you have to remember at some point. Yeah, but it has this form. So if you just try to just multiply two matrices, then that they become identity. Right. Okay, let's move on to something called SO3. So SO3, and the next topic is, let me change the color. So SO3 and next terminology is SE3. These are kind of can be quite scary, but you don't. I will not go deeper. I will not go deep inside. So SO3, it means that means special, S for special, O for orthogonal, 3 for 3 dimension. So SO3 is special orthogonal group in 3D space. So that's just a name. And by definition, SO3 is a set, okay? And it's a set of all 3x3 rotation matrices. So if you collect every rotation matrices, so this is a rotation matrix, right? So if you collect all rotation matrices, then that set is SO3, okay? And interesting fact, or by definition, SO3 is a set of 3x3 matrices such that these conditions are satisfied. Okay, I don't think you really have to know this. Just this is a definition. So any rotation matrix, 3x3 rotation matrix, has the property of this one. Okay, it's transpose times itself is identity. That means the inverse is transpose. And determinant is always +1. Okay. It's a chord group, but I don't think you really have to know it. But just one thing is, if you multiply any two rotation matrices, then that's again a rotation matrix. And by notation, I will use this rotation matrix belongs to SO3. So in the following slides, I use a lot of like SO3 and SE3, but whenever I use something like this, you can just think, okay, this R matrix is a 3x3 matrix and it's a rotation matrix. It's not just an arbitrary 3x3 matrix. It has a special structure and it's a rotation. And if you multiply any two rotation matrices, that's again rotation matrix, which means it belongs to SO3 set. And inverses always exist. So if you have rotation matrix, then if you take transpose, then that's a inverse. Okay. I don't think you really have to do this. I don't think we have to this either. And I think we can just move on. Okay. Similarly, we can define something called SE3, which is called special Euclidean group in 3D space. And SE3 is a set of all every 4x4 rotation matrix. Okay, and I will just say something like that. If I do this, then that means T is a 4x4 transformation matrix. It's just not an arbitrary matrix. It's a special matrix, which is 4x4 transformation matrix. Okay. Here, let's forget about this. Oh yeah. So SE3, if you remember, we have a rotation matrix, translation vector, a 0 and 1, right? And that's 4x4 matrix. And it belongs to SE3. So basically SE3 element, it has a rotation matrix and translation vector, right? So this T transformation can be represented by rotation, its associated rotation, and its associated translation. So it's P here, okay? P, where this rotation belongs to SO3. That means R is a rotation matrix, and this translation is nothing but R3 element in Euclidean space, okay? So studying like mathematical structures of SO3, SE3 is not in the scope of this lecture, so you you don't have to be afraid of it. In this lecture, it's important to know SO3 is a set of rotations, SE3 is a set of four homogeneous transformations. because I'm going to use like terminologies, something like that. Okay. So why do I have to introduce SO3 and SE3? It's because in this course, we have a robotic system, we have a mobile base, we have a manipulator, and at the end of the manipulator, we have something called gripper, right? And we are going to grasp. We are going to grasp an object using gripper, right? So we have to somehow mathematically represent our grasp. We have to represent grasp. And to represent this grasp, we need a rotation and translation. Rotation of this gripper frame and the translation of gripper plane with respect to either robot base frame or rod frame. It depends on you. Okay. So anyways, we have to represent robot grasp. It's called the robot grasp pose actually. And since this consists of rotation and translation, this belongs to SE3. And this rotation belongs to SO3. Right? So that's why we need it. So later we have to go one step further. We have to represent error of SE3. Okay, so here's an object that you want to grasp. So here's the object frame, let's say. Object frame. And here's your gripper. And here we have manipulator and your mobile base. Okay. And here you have a gripper plane, a gripper frame. Gripper frame. Then we have to calculate the error between two frames, because we want to control or we want to move our gripper to the object frame so that we can grasp an object, right? So we have to represent the error of SE3. So let's say we have one rotation, transformation matrix, and another transformation matrix. Then what is the difference between T1 and T2? What's the error between it? Is that T1 minus T2? That's R1 minus R2, R1 minus R2, 0 and 0. Could make sense, right? Because if you have one vector in Euclidean space, another vector in Euclidean space, vector subtraction gives you the difference between 2 points, right? This is R1, that is R2. If you subtract R1, if you do R1 minus R2, then you get difference, right? You get this difference. But if you do this, then this error does not belong to SC3 anymore, because this small r1 minus small r2, this is r3, that's fine. But if you do r1 minus r2, that's not a rotation matrix, right? So this is not a rotation matrix. So this entire thing is not SE3. So you cannot do it. So for given transformation matrix, we always have an inverse, T1 inverse, right? So this belongs to SE3. T2 is still in SE3. So if you do T1 inverse and T2, that's just multiplication of transformation with another transformation. That's again SE3. So this one, this T1 inverse T2 can represent the error or difference between T1 and T2. Okay, similarly, for rotation errors, you should not do R1 minus R2 because it does not belong to rotation matrix. Instead, you have to do R1 transpose R2, which is R1 inverse R2, or R2 transpose R1. Then this is rotation matrix. Okay. Translation is easy. It's in Euclidean space, so you can just subtract two vectors. Okay, that's fine. But rotation and transformation, you have to be careful. Okay, let's move on to the coordinate representation of rotations. Why do we do it? Because rotation matrix, it's a 3x3 matrix, right? It has 9 numbers. A, B, C, D, E, F, G, C, D. It has 9 numbers, right? And keeping 9 numbers is too, it's too bulky, and we want to have more compact representation. Okay, that's something called coordinate representation, and we will see it very soon. Before going further, I have to introduce two things. One is head operator, and another one is a V operator. And head operator maps 3D vector to 3x3 skew symmetric matrix. And V operator is just reverse. It maps 3x3 skew symmetric matrix to a 3D vector. Okay. So if you are not familiar with skew symmetric, here's the explanation. Symmetric is easy. So if you have, let's say, A, X, Y, Z, X, Y, Z, then its transpose is again A, X, Y, Z, X, Y, Z, right? So these two are the same. In that case, A matrix is called the symmetric matrix. And since this is 3x3 matrix, this A matrix is 3x3 symmetric matrix. Then what is skew symmetric? Sometimes called antisymmetric, and it's a matrix that satisfies this one. A transpose is equal to minus A. And to satisfy this, in 3x3 case, the matrix should have this form. So if you do A transpose, that is 0, 0, 0 here, and Z minus X, Y, Z, X minus Y, which is just minus A. Okay, so this is 3x3 skew symmetric matrix. Why do we have minus here? It's just a convention. Okay, just convention. But it's a very important convention actually. Right? But important thing is you have only like 3 degrees of freedom. we have three numbers here, X, Y, and Z, right? So this any 3 by 3 skew-symmetric matrix can be represented using three-dimensional vector. And any three-dimensional vector can be mapped to a 3 by 3 skew-symmetric matrix, right? And these operators are like called hat operator. So this is a vector. So if you put hat, something like that. So something like that, you put hat here, then you get 3 by 3 skew-symmetric matrix. And this is capital A is a skew-symmetric matrix. And if you apply a V operator, something like that, then you get 3 by 1 vector. Okay. All right. So what about rotation matrices? So again, this is a definition for SO3, which is a set of all 3 by 3 rotation matrices. So it's a 3 by 3 matrix, but it should satisfy this one. So I'm not going into details, but this condition gives you 6 constraints. So let's forget about the details. Okay, 6 constraints. So this is 3 by 3 matrix rotation. It has a 9 elements. 9 elements. So it has 9 DOF, 9 degrees of freedom, but 6 constraints. How many degrees of freedom we have? We only have 3 left. That means we can actually represent, let me write, we can represent rotation matrix using 3 numbers. So we need 3 parameters to characterize a rotation. Okay. So there are many ways to represent rotation. Sometimes roll, pitch, and yaw angles in airplanes. Maybe you have heard of roll, pitch, and yaw. Sometimes we use Euler angles. Uniquaternion is actually a 4 number. This is a 4 number representation, by the way. Or exponential coordinate. And in this lecture, we'll focus on this exponential coordinate. Okay. I forgot to mention one thing. So here, one important property, one important fact. Fact is that if you do A cross B, that's a cross product, right? That's actually same as A hat times B, which is this is 3 by 3 skew matrix, and this is again 3 by where A is R3, B is in R3. Okay, so B is 3-dimensional space, 3 by 1, right? So that's again in total 3 by 1, and this resulting vector is the same as A cross B. Okay, that's a very interesting fact, right? We are going to use this property very soon. All right, so just to remind you, we have a rotation matrix, which is 3 by 3 matrix. It has 9 numbers, of course, because it's 3 by 3 matrix. But by definition, a rotation matrix should have 6 constraints. So this number, just 9 elements, I mean, we can represent these 9 numbers using 3 numbers, right? And one way to represent rotation matrix using 3 numbers is exponential coordinate. So let's first see what is exponential in linear differential equations. So let's consider a very simple uh, linear ODE, ordinary differential equation. X dot is equal to A times AX, and this is initial condition. And we all know the solution is exponential, right? E to the xt, e to the at times initial condition. So if you plug this one into here and here, then left-hand side and right-hand side are the same, right? In fact, this exponential can be calculated using like infinite series expansion, right? So there's a typo. 1 plus at squared divided by 2 factorial cube divided by 3 factorial and so on and so forth. What about the system of linear differential equation? That means now x is a vector n by 1. Let's say xt is n by 1, then a is n by n. So that's, we have like several linear differential equations. And if you represent it using a single equation, that's x dot is equal to ax, where factors and matrices are, the scalar is replaced by vectors and matrices. And here's initial condition. And the solution is again exponential. That's a fact. I'm not going to derive it, but that's a fact. Actually, if you plug this one into here and here, then you can see that left-hand side and right-hand side are the same. But you may, I don't know, some of you may wonder what's matrix exponential, right? Maybe it's first time using this matrix exponential, but the definition is the same. So it's can be just extended. One is just identity matrix plus a times t square divided by 2 factorial at cube divided by 3 factorial 4 factorial and so and so. Okay, that's matrix exponential. All right, so if you see this equation, the solution is matrix exponential. Okay, let's then see what's the exponential map. So here's a vector p, and we are going to rotate this p0 vector with like rate of 1 radian per second from time t0 to t is equal to theta. So along axis, unit axis, of course, unit axis omega. So here's omega. In this, along this axis, we are going to rotate vector p0 from time t is equal to theta. Okay. Then what is p of theta? That's the question. Okay. So what's the velocity of the tip? The p dot, that's velocity. And from physics, we all know that p dot, the velocity, is angular velocity cross its position vector, right? So that's omega cross p of t. And since we have omega cross p, that's equivalent to, that's cross product, right? It's equivalent to omega hat times p, right? And this is p dot is equal to matrix times p. It's the same as this case, right? X dot is equal to ax. So that's just a differential equation, a linear differential equation. So the path of the tip, the solution is given by matrix solution is given by matrix exponential. So matrix exponential is by definition just an infinite series, right? And then we can just rearrange the terms. And then another interesting factor is that if you do omega hat cube, that becomes minus omega hat, okay? And this identity is here. And this part is just an infinite series of sine theta. And this one corresponds to 1 minus cosine theta. Okay, so this matrix exponential can be represented in this way. And this one has to be a rotation matrix for two reasons. Okay, the first reason is that if you just calculate this matrix, then it satisfies the requirements. Okay, these requirements. That's the first reason. And the second reason is that this matrix is multiplied to a vector, and then we get another rotated vector. This is a rotated vector. So this matrix is actually rotating a vector in the space. So this matrix has to be a rotation matrix, right? So this expression anyways represents rotation matrix. And this formula is just it's very popular. So it even has a name. It's called Rodriguez formula. And this formula is sometimes called exponential map. Right? So in this exponential map or Rodriguez formula, what you can see is there's omega or W and theta, like W or omega or and theta, right? And here, if you remember, theta is angle of rotation, and that's of course R1, a scalar value, and omega is axis of rotation. Of course, that's a unit axis, and that belongs to R3. That's actually a vector, right? So if you have angle of rotation and the axis of rotation, then you can take a exponential map or Rodriguez formula. Then you get rotation matrix from omega and theta, which is a rotation matrix, right? And therefore, just combining these two, you can just multiply theta and this axis vector, then that becomes R3, right? And we call this value as exponential coordinate. It's a little bit subtle, right? So this exponential map, so if exponential coordinate is given, then we can obtain corresponding rotation using exponential map, right? This exponential map. That's what we did. Then the next question is, can we do opposite? So given rotation matrix, can we obtain exponential coordinate? Can we do opposite or inverse? Okay, that's called log map because it's inverse of exponential. So log map gives you a given rotation matrix, find exponential coordinate in R3. Okay. So let's begin with the Rodriguez formula or exponential map. So this is identity matrix. That's hat operator. So 3 by 3 is Q. That's 3 by 3 is Q square. Here we have sine 1 minus cosine theta, right? It's all 3 by 3 matrices. So you can just calculate it. And this is a rotation matrix. Here we have several observations. So if you subtract this one and this one, then you always get 2 times omega 1 sine theta. Here, omega 1 means the first component, second component, third component of omega, okay? If you subtract this from here, then we always get 2 times omega 1 times sine theta. So R32 means this one, R23 means this one. If you subtract, you always get this. Similarly, if you subtract R31 from R13, then you always get 2 times omega 2 times sine theta. Once again, R21 minus R12, that's always 2 times omega 3 times sine theta. They're very similar, right? So for omega, that's the axis of rotation. The first component is this one divided by 2 sine theta. And the second component is this one divided by 2 sine theta. And the third component is this one divided by 2 sine theta, right? So, and this one can be rewritten as actually this one. So, yeah, so let me start it again. So omega hat can be actually rewritten as rotation minus rotation transpose divided by 2 sine theta. Okay, this matrix. So it's just you can just try it. Okay. All right. The second observation. So this was the first observation. The second observation is that if you calculate the trace of rotation matrix, the trace is by definition, it's addition of all like diagonal elements. So R11 plus R22 plus R33, and that's always 1 plus 2 cosine theta, right? So here we can obtain what's the value of theta. So this one gives you the angle of rotation. And if once the angle of rotation is found, you can find axis of rotation here. Okay. Just to summary, this is the summary. You can just read it. So exponential map gives you rotation matrix from exponential coordinate, and log map gives you exponential coordinate from a rotation matrix. Okay, just inverse relation. Okay, so the last part is manipulator kinematics. So kinematics, so the motivation is as follows. The robot task is performed in 3D space. So we have a robotic system, mobile base, and manipulator and gripper here, and we have object here. So you have to grasp an object in 3D space, right? But the robot can only move in joint space. This joint can rotate, right? So there's discrepancy between two spaces. This 3D space and joint motions. So kinematics gives us a mapping between two different spaces. Two different spaces are 3D space and joint space. So this two joint manipulator gives us a very simple example, a nice example. So here the first joint angle is given by Q1 and the second joint angle is given by Q2, let's say, okay? And here in 2D space, this is two joint robot, so it has only 2D space. Cartesian coordinate of gripper can be denoted by x and y. Oh, here xe and ye. And then what's the xe value? That's L1 cosine Q1, right? Plus L2 cosine this Q1 plus Q2, right? This one plus this one. So xe is just summation of two lengths. What is ye? That's again addition of two lengths. L1 sine Q1, L2 sine Q1 plus Q2. So that gives us a relation between Q1, Q2, and xe, ye, right? So that's position level kinematics from joint position to Cartesian position, right? And you can just differentiate it. Then here you get the velocities in Cartesian velocities. And then here you get joint velocity and a matrix. And this matrix is called Jacobian. But I don't think we are going to use Jacobian in the lecture. But in general, in robotics, Jacobian matrix plays a very important role. So I will just briefly introduce. So position level kinematics is in general a nonlinear relation because this Q1 and Q2 goes into cosine and sine. So that's a nonlinear function. And at the end, we get xe and ye. So there is a nonlinear function, right? So if you take time derivative, we get x dot on the left-hand side. That's Cartesian velocity. On the right-hand side, we get round f round q times q dot using chain rule, right? And in calculus, this partial differentiation round F, round Q, that's called Jacobian matrix, right? And in robotics, when we say Jacobian, it usually means this matrix, okay? So this one is of course a function of Q, this matrix, but it gives you a linear relation for velocity level. So velocity level kinematics, Q dot and X dot can be mapped using Jacobian, right? So for both position level kinematics, velocity level kinematics, this example is very simple to this space, but of course we can extend it to n degrees of freedom n joint robots. For our case, we have 5 degrees of freedom, 5 joints. We can of course do it. It's no problem for us because there are many libraries that solve kinematics for us. Okay, you can just use it. One last topic is forward kinematics and inverse kinematics. So forward kinematics means we want to obtain n effector position or velocity from joint positions. Inverse kinematics is just inverse. Given n effector position, we want to find corresponding joint values. Or given n effector velocity, we want to find joint velocity, corresponding joint velocity. That's called inverse kinematics. So if you want to place your n effector or gripper in this configuration or this pose, this SC3, then what has to be the joint angles for that? Okay, that's the inverse kinematics problem. So in this point of view, the previous slide was about forward kinematics, right? So how do we do inverse kinematics then? So again, given n effector pose SC3, we have to find corresponding joint angles. So in general, this is much harder than forward kinematics. So forward kinematics is actually easy. It's just a geometric addition, geometric whatever, right? Inverse kinematics is hard because in general, we have infinite many solutions. One like easy remedy is to formulate an optimization. And here's one example that you are going to use in the lab session. So we want to minimize the error between forward kinematics and our target end effector pose, this one. And here, forward kinematics is a function of joint angles. And we want to minimize this function, this error, using Q. Okay, that's the optimization problem. This one is SC3. And this one is again SC3. So we have to compare two SC3 components, right? Remember? So here, somewhere, I cannot find it. Yeah, here. So we compared two SC3 elements, right? So we have to compare two SC3 elements. To do it, we define an error function. Okay, so error between two transformations. It consists of error of position vectors and error of rotation matrices. Error of position, that is easy, right? Because position vector is in Euclidean space, and you can easily compare two vectors in Euclidean space. So that is given by this. So subtraction of one vector from another vector. That's again in R3 space. What about rotation error? So rotation error can be written as here we have one thing is anti-factor, one is target. Transpose R target. That's again SO3 rotation matrix, right? This one represents the amount of, not the amount. It's a difference between end-effector rotation and target rotation. But that's again 3x3 matrix. And the problem of having 3x3 matrix is that how can we measure the size of it, right? How do we measure the size? For vectors, we can just take a norm, right? Norm gives you a size of a vector, length of a vector. But the length or size of a matrix is a little bit it's a little bit intriguing, right? So here we just take a log map. So log of REE transpose R target gives you a 3-dimension vector, okay? And then you can take an like standard norm, vector norm to this exponential coordinate. Okay, that's the entire idea. All right, so it's written here. And then coming back to this optimization problem, this F error, this is actually this taking two SE3 components and gives you R6 vector. So at the end, you can take standard vector norm, and we are going to minimize this objective with respect to join angles. That's called least square problem. And we have several tools to solve this problem, off-the-shelf tools. And I think you will see in the lab session. All right, that's it. I think I did a little bit more than I have. I think it's over 75 minutes. But next time I will try to make my lecture short. So in next time, what I'm going to do is I will begin with basic robotic terminologies, and then I'll briefly introduce you pose estimation of objects using markers. And if I have time, then I'll introduce you some recent approaches like reinforcement learning, imitation learnings, and robot foundation models like vision language models and something like that. Vision language action models, something like that. All right, that's it. Thanks for listening. And yep, that's it.